During this experiment, our team analyzed a multi-junction circuit with multiple resistors. The circuit could not be reduced to simple series or parallel equivalence, thus we had to use the Kirchhoff's rules. The junction law is the sum of currents entering a junction must equal the sum of currents leaving. The loop law is the sum of charges and potential around any loop must be zero.
Hello everyone, for the material sections we will be using an interface, the capstone program, and the resistors.
Before we do the experiment, we have to set up the capstone program to measure those results optimally. In the capstone graph, we set the voltage to 7 volts, voltage limit to 10 volt, and current limit to 1.1 ampere, and select the auto checkbox. In this experiment, we're calculating the voltage and the current from the loop of the resistors in the circuit. So after setting up, we are able to calculate the current and the voltage of resistor 1 by setting up like how we did it in the middle or the top left. Um, so on the very front from the picture, that's resistor 4, and on the very behind with brown color is the resistor 1. And the other two are 2 and 3 in series. And this setup um, would give us the voltage and the current of resistor 1. For the second and the third part, we basically had to do the same thing. For the second part, we either had to figure out the current and the voltage of resistor 2 or 3, and we chose resistor 3. And for the third part, we had to do the same thing. We had to do the same thing, which manipulated those formations of the resistors in the circuits, and to find out the current and the voltage of a resistor 4. So these are the results for the resistors that we've measured. For R1, we measured about 5.917 milliampere and 0.77 voltage. For for resistor 3, we calculated 1.076 milliampere and 0.32 voltage or volt. For resistor 4, we calculated 7.531 milliampere and negative 4.29 volts.
Starting with our analysis of the junction rule, we measured the currents flowing through the circuit to verify charge conservation. We found that the sums of the currents going through resistor 1 and resistor 3 equaled 6.99 milliamperes. When compared against our measured value for the current flowing through resistor 4 of 7.531 milliamperes, we achieved a 0% difference based on our current data roundings. This indicates that the flow of charge entering the junction perfectly balances the flow exiting it, confirming Kirchhoff's first law in this setup. We then moved to loop rule A, examining the conservation of energy. Our measured source voltage was 5.06 volts. This matched the combined voltage drops of the voltage going through resistor 1 and resistor 4 exactly, resulting in another 0% difference. This position suggests that our measurement tools were highly consistent for this specific loop, with negligible energy loss detected across these components. Finally, we analyzed loop rule B, comparing the voltage going through resistor 1 against the sum of the voltage going through resistors 2 and 3. Here, our measured values of 0.71 volts was compared against the theoretical expectation of 0.77 volts. This resulted in a 7.79% difference. While this is our largest margin of error for this slide, it remains well within the standard 10% tolerance typical for physical resistors. This small discrepancy is likely due to the internal resistance of the leads or minor fluctuations in multimeter's position at lower voltage ranges.
This is Lab 5 conclusion. So after we did our experiment, just to review some questions that we had at the end of the report, can you create another loop? In this particular experiment, we had an inner and outer loop. We can create another loop. It just would have to be on the inside again, similar to how 1, 2, and 3 were on the inside loop, and then 4 was our perimeter loop. We would create another one on the inside. Of course, the numbers might change because of that, because we would have an additional loop on the inside, but we can always add another loop to the circuit. The differences would come from, like, we would prefer to have our percent error as close to 0 as possible. So for our IR4 and our VE, our percent errors was 0%, because our number that we got in our reading, and the number that was our theoretical number from the values, and the numbers we got from the capstone matched exactly. But for our VR1, that one, there was a slight difference between the capstone and what we theorized. So it was a 7.79% difference. And then that can be due to the actual resistors themselves. They do have different tolerances, that they have that leeway of being 5% more, or up to 5 to 10% more, or less than what they're supposed to be actually doing. So instead of being at the 30%, they could be at 25, or instead of just being at 30, they could be at 35 or similar. So overall, it could just be our resistors themselves, or connections. One of our wires could have been loose, even though that we plugged it in. We can't see inside of the plastic that's covering the wire. So that could also be something like on the inside. Maybe there is something wrong with the wire, and that's why it caused a different reading. Or the clips themselves could be loosened, even though to our naked eye we see them fine. But it could be the equipment that causes that as well. Can you minimize these differences? Yes, we can minimize them, but they will never be 0, because we don't live in a theoretical world. And some energy during the experiment can be lost as heat in the wires. And then the ways to minimize it would be to, instead of using the resistance that is labeled by like the colors or the resistors themselves, it could be using the multimeter. So using the meter to get the actual resistance that that resistor is giving, and using that information rather than just using the color coded numbers to say, oh, this one's supposed to be 760 ohms, but it's actually working at 700. Similar. And then double checking the connections. Again, if it's to the naked eye seems to be working, but on the inside, we could always try to do the same experiment, but with new equipment or different equipment. See if there's a bigger percent error or a smaller percent error. Hopefully it would be smaller, but you never know what if the new equipment you get is broken. And then just to always ensure that we start from 0 on our software capstone. And then that's the conclusion for our lab 5.